So in the last class, we had finished discussing the definition of discrete Fourier transform, and just as a reminder, I want to relate it to the discrete Fourier series definition. The definition we had studied of the discrete Fourier transform goes like this. We are given a discrete sequence, finite duration sequence xn, and we compute its discrete Fourier transform using the formula that we have studied before, xk. But the operational meaning of this discrete Fourier transform goes like this. These discrete Fourier transform coefficients actually correspond to a discrete Fourier series coefficients, which are given by just periodic repetition of your discrete Fourier transform. So you have x tilde of k, and all the operations effectively are happening on this discrete Fourier series. So corresponding to these discrete Fourier series coefficients, you have a periodic sequence x tilde of n. And this xn just corresponds to the one period of that periodic sequence. So n equal to 0, 1, up to n minus 1. And we can also write that as a periodic repetition if the length of the sequence, this period, because it's less than n, the period of this x tilde n is capital N. So that is the relationship. So whenever we have to compute or figure out any properties of the discrete Fourier transform, it's best if we keep this picture in mind. So we go first to the discrete Fourier series by considering these xk's as just one period of the discrete Fourier series coefficients. Then we end up doing whatever we want to do, figure out what x tilde n is. Whatever is one period of that x tilde n will be my time domain inverse discrete Fourier transform. Okay? That way we can figure out the relationship of the discrete time Fourier transform when we are relating discrete Fourier transform and discrete time Fourier transform sequences better. So just keep that in mind, and we had already covered a few properties. Today we'll look at some more properties of the discrete Fourier transform. One property is this symmetry property, or rather properties, which effectively go back to if you are given an even sequence, what does the Fourier transform look like? Or if you are given a real valued sequence, what does the Fourier transform look like, and things like that. So just to remind you, the formal definition of an even function, and the definition is true whether you're talking about discrete time or continuous time, so I'll just use a generic version of that. So an even function is a conjugate reflection about the y-axis which means if I have a function of some variable f of y, then that is equal to f conjugate. If I reflect it around my y-axis, then it's conjugate symmetric. For real valued, it's just the even function that we typically talk about. An odd function similarly is one which is conjugate reflection about the origin. So minus f of y equals f conjugate of minus y. And the examples of this are, of course, the classical, since I'm not going to draw complex version. In real version, that's pretty easy. This is, for example, an even function, and something like this will be an odd function. And then there are other properties, which are that if you are given any function given f of y, it can always be written as sum of even and odd functions. So f of y can always be written as f of e of y, where f of e of y is an even function plus f of o of y, which is an odd function. And the way you derive this is f of e of y can be defined as 1/2 f of y plus f conjugate of minus y, and f of odd, that's half f of y minus f conjugate of minus y. Okay. Now, most of the time, symmetry properties are perhaps one of the least interesting properties if you are doing just learning about a transform. They really sort of shine when you are trying to do some sort of analysis, formal analysis. They simplify the analysis. You can make some, if you know certain properties based upon the symmetry properties, you can really simplify your analysis. And like one of the classical examples of a symmetry property that I'm sure you have studied long time, which is related to the discrete time Fourier transform, is that if x of n is a real valued function or sequence, then its Fourier transform is even. So then x of e to the j omega is an even function of omega. And that really comes from the property that the real of x of n, which is the formal symmetry property, if you take the dtft of that, that is related to the even part of your Fourier transform. And similar version exists even if you are doing continuous time. So that is the reason why we mostly we only plot our discrete time Fourier transform, the continuous time Fourier transform. Whenever we plot them in an even way, because we assume that we are dealing with real valued sequences or functions. Okay. So similar kind of symmetry properties exist in the case of the discrete Fourier transform, but we have to be careful about the meaning of those properties. Okay. For example, you could still, the similar conclusion can be drawn that if you are given a real valued sequence, then the magnitude of your discrete Fourier transform will be even. So the whole discrete Fourier transform will be conjugate even, or it will be even in the conjugate sense, right? Which means if you just look at the magnitude, it will be even. But what is the meaning of that? Which even part that will relate to is different from, for example, what you see in the case of this discrete time Fourier transform. So the example of that is if you are computing real of x of n, the DFT of that is not going to be even part of the DFT sequence of the original of the whole sequence. So if xn had a DFT of x of k, you're not going to simply put xe of k here. And the reason for that goes back to the relationship between the DFT and the discrete Fourier series. To really figure out what does real of x of n mean, you actually have to go back to the discrete Fourier series and try to derive from the symmetry properties of the discrete Fourier series. And we are not going to spend time upon this. I just want to bring it to your attention. In the discrete Fourier transform case, it ends up being actually xep of k, and why we have called it ep, which is strictly not equal to xe of k. Okay, so it's not equal to the even part of your original Fourier transform. It's equal to one period of an even part of the periodic sequence from which you calculated your discrete Fourier series. So remember that you have x of n. If I am doing the discrete Fourier transform, this x of n is actually, this x of k is actually related to x tilde of k, right? So this x tilde of k now can be written as an even x tilde e of k and an odd x tilde e of k. Okay? And this xep of k is actually one period of that thing. It's one period of x tilde ek. Okay? And if you simply just take any example of a periodic sequence, compute its even part, you will find out that in general this is not going to be true. So that's another case if you just don't pay attention to the fact that really when you talk about discrete Fourier transform, that discrete Fourier transform is actually representing one period of some discrete Fourier series. Then you can draw wrong conclusions about properties of your discrete Fourier transform. Okay, so there are other properties of this discrete Fourier transform. The other most common one is that if you take j imaginary of x of n, then in the DTFT world, that is just the odd part of your discrete time Fourier transform. Okay, in the DFT world, that is the odd part of one period. That is one period of the odd part of this thing. Okay, of the odd part of your discrete Fourier series coefficients. So the other properties can be derived in a similar manner, but as I said, mostly they don't. The real sort of advantage of these symmetry properties come when you are trying to do some analysis and they help you simplify things. But here we are not going to spend time discussing them. I just want to bring this aspect to your attention that there is not a one-to-one relationship between whatever properties you see in the discrete time Fourier transform world to the discrete Fourier transform world. Okay, the real relationship is through the discrete Fourier series. So let's start by discussing a more relevant and important property, which is that of circular convolution. So what we are given are two sequences and their endpoint DFTs. DFT of x1n is x1k, and DFT of x2n is x2 of k. And we define another DFT sequence x3 of k as multiplication of the x1 of k and x2 of k. And we are interested in asking what is the time domain sequence that corresponds to this DFT sequence. So what is x3 of n? That is the question we are asking, corresponding to x3 of k. Okay. Once again, to answer that, we should really translate x3 of k to the discrete Fourier series world by we build discrete Fourier series coefficients corresponding to periodic repetition of that. We get x3 tilde of k. Okay. And these x3 tilde k's now will have some periodic sequence associated with them, which will be x3 tilde of n. And this x3 tilde n, when we extract one period of that, so we compute n equal to 0, 1 up to n minus 1, and that will give answer to what is x3 of n. Okay. So let's then follow this this sort of plan, which is we start with x3 of k and we construct x3 tilde of k. So x3 tilde of k is simply periodic repetition of x3 of k, which is simply periodic repetition of x1 of k and x2 of k. Now each one of these is just the discrete Fourier series associated with x1 sequence and x2 sequence. So this is the discrete Fourier series x1 tilde of k, and this is the discrete Fourier series x2 tilde of k. So we are interested in finding out the periodic sequence x3 tilde of n that corresponds to multiplication of x1 tilde k and x2 tilde k. Now that we did as a property of the discrete Fourier series. We said if you multiply two discrete Fourier series coefficients with each other in the time domain, that is equivalent to periodic convolution of the time domain periodic sequences. So what we really have is that we are interested in finding out what is the discrete Fourier series of x1 tilde k and x2 of tilde k. And from the properties we saw that that is simply periodic convolution between x1 tilde of n, and I'm going to use just this notation, x2 tilde of n. Okay. So if we want to find out remember our goal is we are interested in x3 of n, which is just one period of x3 tilde of n. So what we will do is compute x3 tilde of n and then write down its one period. Okay. So if we remember our definition of periodic convolution, we said it looks exactly like linear convolution. You have x1 tilde of m, x2 tilde of n minus m. The only difference in periodic convolution and linear convolution is where does this summation over m go from? In linear convolution, this summation goes from minus infinity to infinity. In periodic convolution, it goes over one period. So without loss of generality, we'll take it m equal to 0 to n minus 1. Okay. Now this x1 tilde of m, we start putting in the values, right? So this, again, if you go back to the picture, the time domain sequences are related through periodic extensions. So this x1 tilde of m is nothing but periodic repetition of x1 of n, right? And x2 tilde of n is simply periodic repetition of x2 of n. So we just plug those values in. We get summation m equals 0 to n minus 1. x1 m mod n and x2 n minus m mod n. Now m is going from 0 to n minus 1, so m mod n equals to m as long as my m is between 0 and n minus 1. Just the simple fact of mod. So for all m equal to 0, 1 up to n minus 1. If I stay within one period, the mod operation does not do anything. So I just replace that m equal to 0 to n minus 1 x of m, x1 of m, x2 of n minus m mod n. Okay, this is x3 tilde of n, which means that x3 of n, which is just one period of that, is simply the same thing x1 of m, x2 of n minus m, mod n, but now we are only limiting ourselves to n equal to 1, 0, 1 up to n minus 1. Okay. This thing is called circular convolution, written as x1 of m n There are different notations. Your book uses this notation, x1 of n, circular convolution with x2 of n, and the circular convolution is an endpoint circular convolution. So we'll come back to understanding this, but just to say the property then clearly, we have that if we multiply the DFT sequences of two time domain sequences, finite duration, that is equivalent to doing circular convolution in the time domain. Okay. Now let's interpret the circular convolution. Again, the structure is very similar to convolution. So what you get is you fix one sequence, so x1m is fixed. The other sequence, it's n minus m with mod. So you circularly flip it. Okay, instead of flipping it, you circularly flip it, and then you circularly shift it for different values of n, and then you sum up over all m's, and that's your end result. Okay. So in linear convolution, you fix one sequence, you flip the other sequence. In circular convolution, you circularly flip the other sequence. Okay. What I mean by circular flip is if I am given a sequence x2 of n, the circular flip is x2 of minus n mod n. Okay, this is circular flip. And then you circularly shift it by different values. So in linear convolution, you linearly shift it, and then you multiply the two sequences and add them up. In circular convolution, after doing the circular flip, you keep on doing the circular shift. Okay. So we'll look at it pictorially also, but there is one classical example that everyone should know at the top of their head for circular convolution. So assume that x1 of n is simply a direct delta. It's delta of n minus n naught for some n naught between 0 and n minus 1. Okay. So if I were to compute x3 of n as x1 of n convolved linear convolution now with x2 of n, which is delta of n minus n naught x2 of n convolution. What is the answer of that? When we convolve a sequence or a function with an impulse, shifted impulse or a shifted direct delta, what happens to the resulting sequence? We just get a sequence which is shifted to the location of the direct delta. So linear convolution with the direct delta gives us a sequence which is simply shifted to the location of the direct delta, right? Or which is linearly shifted to that location. Let's look at what does circular convolution with the direct delta do. So now we are interested in computing x3 of n as x1 of n, circular convolution with x2 of n. So we simply plug in the formula m equal to 0 to n minus 1, x1 of m, x2 of n minus m mod n. Now x1 of m is 0 for all m except at m equal to n naught, right? That's the definition of this direct delta, that this is equal to 1 for n equal to n naught and 0 otherwise. So x1 of m is 0 for all m's except at m equals to n naught. So at m equal, so all these summation terms will be 0 except at m equal to n naught, and at m equal to n naught it will be equal to n minus n naught mod n. So what does circular convolution with a direct delta do? It circularly shifts your sequence to by the amount at which where the direct delta is located. Okay, so linear convolution, you get a linear shift at the location. In circular convolution, you get a circular shift at that location or by that amount. Okay, this is an example where your x1m is simply equal to delta of m minus 1. Okay, so a direct delta at location 1, and you want to circularly convolve this sequence with this sequence. You can go through the expression, but in reality what's going to happen is that all of this thing is going to be circularly shifted by an amount of 1. So you move these things here, and whatever sticks out at the end, if you remember your circular shift formula, this thing simply will go here. Everything gets shifted by 1, and the last one comes back, right? Because it's shift by 1. And so your final answer will be simply this, right? This is all the entries get shifted, but the final one, instead of being at n, which you would get at in the case of a linear shift, simply comes back to 0. Okay. Here is another example of circular shift where you are given two rectangular sequences of length n minus 1 each. Okay. And the way you will do the circular convolution is simply you will fix one sequence, right? So you fix x1n. These are your two sequences, x1n, x2n. You fix this. You first circularly flip the other. Now in linear convolution, you are going to linearly flip it. You circularly flip this, this is the circular flip. Which is simply x2 minus n mod n. And if you remember, minus n mod n is simply n minus n for n not equal to 0. Okay, and it is equal to 0 for n equal to 0. So it's a very simple operation. Circular flip is whatever is at 0 sort of stays at 0, but everything else gets moved to n minus n location. So whatever is at 1, this gets moved to n minus 1. This gets moved to n minus 1, this gets moved to n minus 2, and so forth. So this is the circular flip operation. And after the circular flip, now you are going to, for each new value that you want to compute for n, you circularly shift by that amount of n. Okay? So you shift it, for example, this is a shift by 2, circular shift by 2, which means that you are going to keep on moving things here, and everything, you cannot go beyond n, right? So when you shift by 2, two of these things will move here, this will move by 2, and so forth. And the final answer that ends up being is depends upon the value of n. Okay, so if your n, so there are effectively two examples in the same thing. If your n ends up being the same as the length of your sequence, so this is the case where your length of the sequence is n and you are doing circular convolution by n, then this is your answer of the circular convolution. Okay, and if you actually increase your length of n, you make it double the length of your sequences, then actually you get back this triangle, which is sort of the sequence that you would get if you were to do linear convolution. Okay, so we'll come back to it, that why under what condition the circular convolution will be equal to the linear convolution, because in these two examples, the same sequences in one case, so these are the two sequences. If I do circular convolution with n equal to the length, I get this. But if I use a big enough n, which is specifically, say, twice the length of the sequence, then I actually get back a circular convolution which looks similar to the linear convolution. Okay, even though the way you arrived at this is through a different process. You arrived at this through doing circular flipping and circular shifting. Okay. The end result is same. You need to keep in mind that it is not that the steps that you are taking within those are same. But the end result ends up being same if you use a certain value of n, which is big enough. So we'll look at that condition, what makes that, under what conditions the answer of circular convolution ends up being the same as that of linear convolution. So here is a summary of the properties of the discrete Fourier transform. The main one is this linearity property, which is that discrete Fourier transform, just like all the other transforms, is linear. You can, if you add up sequences, the Fourier transform is simply the linear combination of the sequences. This is the duality property that we had done. This is the property that if you do, whereas in discrete time Fourier transform, if you multiply with a phase shift in the frequencies, you get a linear shift in time. This is circular shift in time. So if you multiply your DFT sequence by this phase, that is equivalent to doing a circular shift of your sequence. Okay, and by the duality property, then you have an according version here. This is the property that we just did, which is that if you multiply, so this is the circular convolution property, that if you multiply two DFT sequences, that is equivalent to doing circular convolution of the two sequences in time. And by the duality property, then you have this equivalent version which says that if you multiply two sequences in time, then because of the duality property, you have actually circular convolution of the DFT sequences with, of course, the 1 over n factor due to the uneven nature of DFT that we are doing. Remember, we are not doing orthonormal DFT. We are doing orthogonal DFT. Okay. And the rest of these properties are more related to the symmetry properties. I talked about those. You should read it up. They are really helpful, as I said, sometimes when you try to do some sort of analysis. They can really simplify your analysis. But we are not going to talk about them too much. Now what we are going to try and do is derive the relationship between linear convolution and circular convolution. Specifically, what we want to ask is, when is the linear convolution, or when is the answer of circular convolution equal to the linear convolution And while answering that, we want to specifically understand, is there a deeper relationship between linear convolution and circular convolution, other than just saying that if you look at these equations, they look very similar. Instead of doing linear flip, you do circular flip. Instead of doing linear shift, you do circular shift. Is there a more deeper relationship between the two? So what is the relationship between the two? In the sense of, let's say I just give you a circular convolution of two sequences, linear convolution of two sequences, without you having to do really an extensive calculations, or even without having to look at the individual sequences. Can you just, for example, tell what the circular convolution would have been? Okay, and that answer follows if you understand the relationship between the circular convolution and linear convolution. So to answer this, we'll start with two sequences. We'll say we are given two sequences, x1 of n is of length capital L, which means that x1 of n will be equal to 0 for all n naught between 0, 1 up to n L minus 1. Okay. It may take other 0 values within this, but outside this it is definitely 0. And then the other sequence, x2 of n, is of length p. So x2 of n is 0 for all n, sorry, it is not n, so for all n naught in 0, 1 up to p minus 1. And we are given the linear convolution x3 of n, which is equal to x1 of n and x2 of n. And we are interested in finding out what is the relationship of this x3 of n to, is there a relationship between that? And since now I have 2x3 of n, I'm going to call the circular convolution answer as x3p of n, which is x1 of n, circular convolution with x2 of n. Okay. So no longer the sort of superficial relationship, we want an exact relationship. That if I give you linear convolution, how would you, for example, calculate the circular convolution using this relationship? Okay. Now the first thing we want to derive is what is the length of x3 of n. We are taking linear convolution of two finite duration sequences. We get another finite duration sequence. And many of you probably will already know the answer, but still let's just go through the formal process. So we have m from minus infinity to infinity, x1 of m, x2 of n minus m. Now since x1 is 0 for everything outside 0 to L minus 1, I can change this summation to m from 0 to L minus 1, x1 of m, x2 of n minus m. Now, x2 of n minus m is going to be 0 for all m in this summation, for all m belonging to 0, 1, up to L minus 1, whenever n is greater than or equal to L plus p minus 1. Okay? Whenever your index n is bigger than the length of one sequence plus the length of other sequence minus 1, x2 of n minus m will be 0. And if it will be 0, then this whole summation will be 0. Okay? So this means that x3 of n will be equal to 0 for all n greater than or equal to L plus p minus 1. Okay. And the same will be true if you do n less than 0. x3 of n will also be equal to 0 for all n less than 0. So that's the usual sort of relationship that you learn in your undergraduate, which is that if you take convolution of two, for example, continuous time signals, then the length of the convolution is the sum of the length of the two. If you take convolution of two discrete time sequences, then the length of the convolution is the sum of the length of the two minus 1. Okay? So this means that x3 of n is of length L plus p minus 1. Okay? x3 of n is 0 for all n not in 0, 1 up to L plus p minus 1. So this is a critical thing that we need to keep in mind, and we'll come back to it now. Now, let's figure out what does circular convolution mean in terms of sampling of the frequencies of the sequence corresponding to the linear convolution. Okay? Remember that we talked about sampling, the way we derived the DFT. Before that, we had a small section where we talked about sampling the DTFT of a sequence. And we'll try to exploit that. So just as a reminder, we had talked about, and I'll use the x3 of n here. We had talked about that if we have DTFT of a sequence given by x3 of e to the j omega, and if we take samples of the sequence, if we take n samples of the sequence, so we sample the frequency domain, then those samples can be associated with a discrete Fourier series, with the coefficients of a discrete Fourier series. Okay, so these samples, if I take samples of these, sample at omega k equal to 2 pi k over n, I call that x3 tilde of k. Okay, the samples of this discrete time Fourier transform can be associated with a discrete Fourier series coefficient sequence, and these DFS coefficients have a corresponding periodic sequence x3 tilde of n, which is given by this x3 tilde of n we had talked about is given by periodic repetition of our original sequence, where the repetition is with the period n. So we had talked about that is equal to r from minus infinity to infinity x3 of n minus rn. Okay. So that was one of the, when we had started discussing the relationship between the discrete Fourier series and the discrete time Fourier transform, that is one of the key expressions that we had derived. We had said that just like you can do sampling in the time domain, you can do sampling in the frequency domain, and the samples correspond to a time domain periodic sequence which is given by periodic repetition, and the only time you can recover the original sequence from this periodic repetition is if the length of the sequence is smaller than the period capital N. Otherwise, you will have what we call time domain aliasing. Okay? So based upon that, we want to derive the relationship between the circular convolution and the linear convolution. So we'll have to keep both things in mind. x3 of n is x1 of n linearly convolved with x2 of n. What is the discrete time Fourier transform of that? The discrete time Fourier transform of linear convolution is multiplication of the discrete time Fourier transform. So x3 of e to the j omega is equal to x1 e to the j omega times x2 e to the j omega. So far we haven't done anything too difficult. It's just we have just related the old knowledge. Now we sample this x3 e to the j omega. So sample this x3 e to the j omega, take a total of n samples. So sample this at omega k equals 2 pi k over n. What do we get? We get x3 tilde of k, which is equal to x3 of e to the j 2 pi k over n, right? Which is equal to x1 e to the j 2 pi k over n multiplied by x2 e to the j 2 pi k over n. Now these discrete Fourier series coefficients, as I wrote above, have associated with them a discrete time periodic sequence x3 tilde of n, which is simply periodic repetition of x3 of n, the linear convolution minus Rn. Okay? So, but what is the relationship of the circular convolution X3EP? So X3EP, if you remember, X3P of n, which is we had defined as X1n, circular convolution, endpoint circular convolution with X2 of n. In DFT domain, that is equal to, it has X3P of k, which is equal to X1 of k and X2 of k. Okay? But what is X1 of k? Because of the relationship between DFT and discrete Fourier series and DTFT, what is X1 of k? Simply samples of the DTFT of X1 e to the j of X1n. So this X1k is nothing but X1 e to the j 2 pi k over n. This X2k is nothing but X2 e to the j 2 pi k over n. Which means that the relationship between X3p k and X3 tilde k is that of simply periodic repetition. A simple, this X3pk is one period of this discrete Fourier series. This is just one period of that. So if we have a sequence which is one period of the discrete Fourier series coefficients, then in the time domain, what is the relationship between the periodic time domain signal and the non-periodic aperiodic discrete Fourier inverse discrete Fourier transform sequence? They are also related to each other through one period. If these are the discrete, I am looking at the discrete Fourier transform. These are my discrete Fourier transform coefficients. These coefficients are given by just one period of some discrete Fourier series coefficients. If that is the case, then at this time domain part, the relationship between X3Pn and X3 tilde is that this is just one period of X3 tilde n. Okay. This is just the old diagram that I had drawn. Up to this point, this part of the whole block diagram is something that we have discussed many times. This is just the relationship between the discrete Fourier series and the discrete Fourier transform. The discrete Fourier transform coefficients here correspond to one period of X3 tilde k. So the corresponding time domain signal must correspond to one period of X3 tilde n. That is one side of the picture that you need to have clear in your mind. If that is clear, now from the other relationship between sampling of the DTFT and discrete Fourier series gives us this block. Which says that these discrete Fourier series coefficients come by sampling the product of two DTFTs. So this X3 tilde n is actually just a periodic repetition of your linear convolution. So based upon that, you can say that the relationship between the circular convolution and the linear convolution is that circular convolution, you first draw a periodic repetition of your linear convolution by a period of n, and then look at the main period of that. That will be your answer to the circular convolution. Effectively, your circular convolution is just time aliasing of your linear convolution. So your circular convolution x3p of n is just one period of x3 of n. X3 of is one period of r from minus infinity to infinity, x3 of n minus rn, where x3 of n is the linear convolution. Effectively, if your linear convolution, let's say this is 0, this is n, this is minus n. Let's say your linear convolution ends up being, and I'm now not going to draw a stem plot because that will take me a longer time. Let's say that my linear convolution is this plot. So stem plot of this is the envelope of my plot. Okay? My circular convolution corresponds to periodic repetition of this sequence. So I get one here. Another version of this same thing will be here. Another version of the same thing will be here. Okay? And what you are going to see is whether or not you have this overlap, right? Whether this thing overlaps depends upon what is n in relation to the length of your linear convolution. So what is this endpoint? This is L plus p minus 1. We talked about linear convolution is of length L plus p minus 1. So when will these things overlap? If n is less than L plus p minus 1, then we will have a figure like this. And we will then look at the principal period of this thing, which is still between 0 and n. So the principal period of this thing is still between, I'm still looking at between 0 and n, and my circular convolution will not look like this at all. It will look like something like this. Okay. Up to n, sorry. So this will be my circular convolution if my n is less than L plus p minus 1. But if I did not have this overlap, then my circular convolution, there will be no time aliasing of my linear convolution, and my circular convolution and linear convolution answer will be exactly the same. So the upshot is that circular convolution is given by time aliasing of the linear convolution. And the aliasing will happen if n is less than L plus p minus 1, which is the length of my linear convolution. Then aliasing will take place. And x3p of n is not going to be equal to x3 of n. But if n is greater than or equal to L plus p minus 1, then x3p of n, which is the circular convolution, is equal to x3 of n. Okay. So in general, if you want to compute the circular convolution, you don't even have to look at the individual sequences if you are given the linear convolution. All you have to do is just do aliasing. Okay? But now you're doing aliasing of the time domain signal. You just put one copy at 0, another copy at n, another copy at minus n, add all of them up, and then look at between 0 and n. Okay? And if you know that n is bigger than L plus P minus 1, then don't even bother doing that, because you know that the circular convolution will be equal to the linear convolution. So here is an example of showing circular convolution as a linear convolution with time aliasing. So you are given two sequences. It's the same set of sequences that we saw before, just rectangular pulses with length 6. This is your linear convolution. Okay. Your linear convolution of rectangular sequence is just this triangular signal. And if you want to compute the circular convolution, you put one copy at 0, put another copy at n. So this is the copy of x3 at n, x3n minus n. Put another copy at minus n. Okay, and then add all of them up, and just look at the time between. Just look at the period between 0 and n minus 1. So if you add all of them up, okay, they are not perfectly aligned. This 0 is here and here. Okay. So if you add all of them up, you get back this sequence. Basically, this thing is decaying, but this thing is growing, and they are both linear, so you get a constant. And similarly, this thing decays and this thing grows, and again you just get a constant. Okay, so this is your circular convolution. By just adding those three copies, you don't have to extend far enough if your n is not that small. Okay? Now I can do the same thing if I increase my n, right? Then the same thing, if I do, I will not have actually an overlap. So this is for the case when n equals to 6. Okay, your circular convolution looks very different from the linear convolution. But now, since I am taking n equal to 2l, l was the length of my sequence, which is, of course, bigger than or equal to 2l minus 1, which is the length of my linear convolution. In that case, my circular convolution and linear convolution will have the exact same answer. Okay. Coming down, here is a more sort of uneven signal. x1n is this, x2n is this is LP. So if you compute the linear convolution, this is what the answer comes out to be. Okay. The length is L plus P minus 1. It goes from, and you to compute the circular convolution, now you again do the same thing. You have one copy at 0. You generate another copy at minus L. So they are taking n equal to L. Another copy at L. You add all of them up, and then just look at between 0 and L minus 1. And if you do that, then this is what the answer comes out between 0 and L minus 1. Doesn't look at all like the linear convolution, but indeed it is obtained by adding these three copies together, by aliasing of these three copies, and then looking at between 0 and L minus 1. Okay? So that's another interpretation of circular convolution which is just aliased version of your linear convolution. And thinking of it that way also tells you when they will be both equal. Okay? And why do we care about this? Because in digital systems, we hardly do convolution, especially in real-time systems. We don't end up doing convolution, linear convolution, by writing the explicit convolution sum. We do it through the discrete Fourier transform, because discrete Fourier transform has a much faster implementation. And if we do a discrete Fourier transform, then we are effectively doing circular convolution. So then we better make sure that the answer of our circular convolution matches the linear convolution.